Hello students, once again welcome to the exciting world of electronic device and circuits. In the previous two lectures, I have explained about introduction to the course, and then later I have explained about category of materials. Generally, materials that are available in the real world are categorized into three types: conductor, semiconductor materials, and insulators. Our course is all about semiconductor materials, silicon and germanium. And later on, I have explained about pure silicon and germanium materials. Pure silicon and germanium materials behaves like insulators at absolute zero temperature. At room temperature and certain range of temperatures, they behave, they exhibit conductor properties. And if you further improve if the temperature is higher and higher, beyond 400 degrees Celsius and 500 degrees Celsius, they again behave like insulators. Our whole subject is about understanding the semiconductor materials and formation of N-type and P-type semiconductor materials, construction of diodes, transistors, FET using the semiconductor materials. So semiconductor materials are categorized into two types: pure semiconductor materials and extrinsic semiconductor materials. Pure or intrinsic semiconductor materials are pure form of silicon, germanium. Extrinsic semiconductors are impurity semiconductors that are formed by adding certain impurities. So in the today's lecture, we discuss about impure semiconductor materials or extrinsic semiconductor materials. The lecture objectives of the today's session. After this lecture will develop students' knowledge on classification of semiconductor materials, lecture objective 1. And lecture objective 2 is you will understand and you will get the knowledge on extrinsic semiconductor materials formation. Semiconductor materials are classified into intrinsic or pure semiconductors, extrinsic semiconductors, or impure semiconductors. We can form these extrinsic or impure semiconductors by adding certain impurities. If you add third group elements to the pure silicon, it forms P-type semiconductor material. If you add fifth group elements to the silicon and germanium, they will form N-type semiconductor material. In the N-type semiconductor material, electrons are the majority carriers. In the P-type semiconductor materials, holes are the majority carriers. Extrinsic semiconductor or doped semiconductor or impure semiconductors are formed by adding impurities. Impurities plus pure semiconductor is known as extrinsic semiconductor material. Let us consider I have taken a phosphorus material, phosphorus impurity. It is a fifth group element. By adding fifth group element phosphorus to the pure silicon material, N-type material is formed. When aluminum material, third group element is added to the silicon material, then it is known as P-type semiconductor material. Pentavalent group are the fifth group elements: phosphorus, arsenic, antimony, and bismuth. When they are added, when you add these pentavalent group elements to the semiconductor, pure semiconductor, N-type semiconductor materials are formed. When you add the trivalent group elements like boron, aluminum, gallium, indium, and thallium, it generates P-type semiconductor material. What is doping? The process of adding impurities to the pure silicon material is called doping. So when phosphorus is doped with pure silicon, N-type is formed. When aluminum, third group element, is doped with silicon, then P-type semiconductor materials is formed. If there is no doping, if it is a pure silicon, the conduction is very, very pure, 1 microampere. When very small amount of phosphorus is added to the pure silicon, then its conductivity is improved. When impurity content is improved, when the impurity amount is improved, if you add more impurities to the pure silicon, then you will get better conductivity property from the semiconductor materials. You can observe these three cases. No doping, very pure conduction of electricity, 1 microampere. When little bit doped, lightly doped, then 1 milliampere conduction current is generated. When heavily doped, doping is heavy, then conductivity is better now, it is 5 milliamperes. What is a doping profile? Doping profile means how many impurity atoms that they are adding to the pure atoms. For example, one element, one atom impurity is added to the 10 to the power of 8 silicon atoms, then we call it as 1:10 to the power 8 doping profile. If the doping profile is 1:10 to the power of 8 means for every 10 to the power of 8 silicon atoms, for every 10 to the power of 8 silicon atoms, one impurity atom is added. One impurity atom is added for every 10 to the power of 8 silicon atoms. If the impurity is a fifth group element, phosphorus, then it is N-type material. If the impurity is a third group element, then it aluminum, then it is known as P-type semiconductor material. Yes, you can see now for every 10 to the power of 8 pure atoms, pure silicon atoms, one impurity is added here. Okay. Yes. And types of doping profiles, lightly doped. Lightly doping means for every 10 to the power of 8 atoms, pure atoms, one impurity is added. Moderately, heavily doped means for every less than 10 to the power of 5 purity atoms, one atom is added. Moderately doped means doping one element, one impure atom is added for every 10 to the power of 5 to 10 to the power of 8. Between 10 to the power of 5 to 10 to the power of 8 atoms, one impurity element is added. Lightly doped means the doping profile is 1:10 to the power of 8. Heavily doped means the doping profile is 1:10 to the power of 3. Moderately doped means 1:10 to the power of 5. Pentavalent impurities to the pure silicon, phosphorus is added, then it is N-type semiconductor material. Yeah, this is a doping profile. You can observe here 1:10 to the power of 8 here. Now, here, let us look into that. What are the majority carriers in N-type semiconductor materials? Now, this is a pure crystal of silicon. Now, these are the covalent bonds. When pure silicon is crystal is there, then automatically covalent bonds are formed between adjacent silicon atoms. Now, the crystal becomes stable, and all the atoms are stable now. And when fifth group element with 5 electrons here, 5 electrons are added to the pure silicon material. Now you can observe one silicon material, silicon atom is replaced with one fifth group phosphorus atom. Then these 4 red electrons form covalent bonds with the 4 yellow electrons, but one electron is free now here. You can observe this is the first covalent bond formed, this is second covalent bond, third covalent bond, and fourth covalent bond. And now see this. This is the fifth electron, which is a valence electron, which can be easily detached. That way we can improve the conduction process. And here, this fifth group, this fifth electron is having higher energy levels because it is not in the covalent bond. Which are in the covalent bond will have lower energy levels, and the electron which is not participating in the covalent bond is having the highest energy levels, and it is placed to the Doran energy level E suffix D. E suffix D is the energy level which is formed after adding the fifth group element to the silicon material, silicon atoms. Now the new energy level is obtained here. This is called as donor energy level E suffix D. And now, so we can easily move the electron from donor energy level to conduction band, which is electrons which are free in the conduction band only contribute to the electricity. Okay. with a simple 0.05 electron volts energy. If we externally apply, we can shift this electron from donor energy level to conduction band. Okay, these the fifth electrons. These are the fifth electrons which are contributing the electricity when they are moved to the conduction band. Okay, so now the conduction band, even at absolute temperature, even at absolute zero temperature also, the n-type semiconductor behaves like a perfect insulator, but still electrons are not detached. Still electrons are in the donor energy level ED only. We have to move to the conduction band. Then we have either by improving the temperature or by increasing the temperature, or by applying the external force, we can move the electrons in the electrons which are in the uh, donor energy level. We can move them to the conduction band, or we can move the valence electrons to the conduction band. Thermally generated electrons and donor atoms, electrons generated due to impurities also contribute to the electricity. So this is about n-type semiconductor materials. These are now one covalent bond is broken. Here these electrons, these yellow color electrons are indicating these are from impurities, and this is when one covalent bond is broken, one electron from valence band will also move to the conduction band. And now when two covalent bonds are broken and two electrons are moved to the conduction band, in that way conductivity is because of thermally generated electrons and as well as electrons which are due to impurities. The p-type semiconductor material, when aluminum material, which is third group element, is added to the pure silicon, now we can form the p-type semiconductor material. Trivalent group elements such as boron, aluminum, gallium, indium, when they are added to the pure silicon, then it forms a p-type semiconductor material. So doping profile, as I told, one aluminum atom added for every 10 to the power of 8 silicon atoms. That's why we call the doping profile as 1:10 to the power of 8. Now you can see the number of aluminum atoms required. It depends upon the conduction process. If we improve the conduction process more, so we have to add more impurity atoms. Now we can look into this. For p-type, the outermost cell will have aluminum or third group elements will have 3 electrons only at the outermost cell. At the outermost orbit, the aluminum and third group elements will have 3 electrons here, are having 3 electrons. And when you replace one silicon atom, we will replace this silicon atom with this aluminum atom here. When you replace this, so 3 covalent bonds are found between 3 red electrons and 3 yellow electrons, but there is a vacant covalent band here. This absence of electrons in this covalent bond is known as hole, H-O-L-E, the absence of electron in the fourth covalent bond. Here we can observe this, there is a vacancy in the covalent band. This vacancy of electron here, it is known as a hole. This is the hole. So in the p-type semiconductor material, holes are existed in the valency band. Then when you apply the thermal energy, then electrons from other covalent bonds move towards the hole, and in that way holes are moving in the left side and electrons moving in the right side. Then whole electron movement leads to the hole movement, and that leads to the current that will also contribute to the conduction process. Now, because after adding these holes, then another accepted energy level is formed, which is just above the valence band. One more energy level is added here. This is the acceptor energy level here. Okay, this is for p-type semiconductor material. The energy band diagram is like this. For p-type semiconductor materials, holes are the majority carriers. These holes are placed at the acceptor energy levels. When temperature is increased or external energy is applied, these electrons from the valency band are moved to the acceptor energy level, and in that way the whole electron and hole movement will be generated, and that leads to the conduction of electricity. So generation of charge carriers in p-type are charge carriers contributed from impurity atoms, and charge carriers contributed from the thermally generated holes. This is all about extrinsic semiconductor materials. So extrinsic semiconductor materials are impure semiconductor materials. Here we are adding certain impurities to the pure semiconductor material. When fifth group is added, electrons are the majority carriers. When third group elements are added, in holes or the majority carriers. So this lecture learning outcomes of this particular topic is, on listening to this lecture, students will be able to classify semiconductor materials into two types, intrinsic and extrinsic. Students will be able to identify, student will be able to explain what do you mean by p-type semiconductor material and n-type semiconductor material. In the next class, we will look into the certain energy band diagrams of n-type semiconductor material and p-type semiconductor material, and then we will look into what is the current contributed by n-type semiconductor material and p-type semiconductor material. What is the current generated by the electrons and holes, that we will look into in the next class. Thank you.